Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 6.1 and looking at linear systems of differential equations. In Chapter 6, we investigate methods for finding solutions of linear systems of differential equations, using the methods of linear algebra and vector spaces from Chapter 5. Chapter 6.1 introduces the theory of systems of DEs. Then Chapter 6.2 and 6.3 introduce methods for solving systems of DEs. A typical linear systems of DEs can look like this. This particular system is three differential equations in three different functions. This system can be written in the matrix form x prime equals ax, where the matrix A represents the coefficients of the variables x, y, and z. So if we let the vector x be the functions x, y, and z, then x prime is going to be your left-hand side, and the right-hand side can be written as the product of your coefficient matrix times your variable x. We seek to find a vector of functions x of t, y of t, and z of t that will simultaneously satisfy this system of differential equations. Again, this is a skill we practice in Chapter 6.2 and 6.3, but for now we can develop the underlying structure of the solutions. Let's look at a first example. Consider the vector of functions 2e to the 2t, e to the 2t, and e to the 2t. So here this would represent our three functions, x of t, y of t, and z of t. We want to show this is a solution to the system of equations. And to be a solution, it must satisfy the differential equation, meaning that the left-hand side is going to equal to the right-hand side. So let's start by evaluating the left side. On the left side, we want to find the derivative of our x vector. This would be the same as finding the derivative of x of t, y of t, z of t. And we can just take the derivative of this vector. The derivative of 2e to the 2t is 4e to the 2t. The derivative of e to the 2t is 2e to the 2t. And the derivative of the third component, z of t, is 2e to the 2t. And now we'll focus on the right side. And I could plug the vector of functions into the right-hand side given in our original system of equations, or I can plug it into the matrix version. They'll yield the same result. But here, I'm going to plug it into the matrix version. So the right side. The right side is going to be the matrix A with coefficients -3, -2, 0, 1, 0, 0, -1, 1, 3, times our vector of functions 2e to the 2t, e to the 2t, and e to the 2t. Now multiplying these two matrices as we've done in the past would be multiplying this first row of the matrix A times this column, adding up these products as you go. So this would look like three times 2e to the 2t minus 2 times e to the 2t plus 0 times e to the 2t. Our second row, our second entry would be the second row of the matrix A times this column. So this would be 1, 2e to the 2t plus 0 e to the 2t's plus 0 e to the 2t's. And similarly, our third entry would be the third row of the matrix A times this column. So it would be negative 1 times 2e to the 2t plus 1 times e to the 2t plus 3 times e to the 2t. Notice how this gives the same result as if we would have plugged it into just our original system of equations. And now we can simplify by adding like terms inside these inside this matrix. This would be 6e to the 2t minus 2 is 4e to the 2t plus 0. So just 4e to the 2t. This would be 2e to the 2t plus 0 plus 0. And our last entry would be negative 2 plus 1 plus 3. And I believe that's also going to be 2e to the 2t. Notice that the left side and the right side are the same, which shows that this vector of functions will satisfy this system of differential equations. Now, the superposition principle for homogeneous linear systems says if given several functions or several vectors, x1, x2, xn are each solution vectors for the homogeneous system x prime equals ax, then any linear combination of these is also a solution for any real constant c1, c2, and cn. So it's saying that if you can come up with a set of solutions, any linear combination of them is a solution. This is the same superposition principle we looked at previously. So here, if we are given three solutions of the system x prime equals ax from our first example are below, let's write the general solution to this system of equations. Now again, we're just given these for now. How we actually find them, that's something we'll look at in chapter 2. But if these are each solutions, Then a general solution x, the vector of t, could be c1 times your first solution c2 times your second solution vector and c3 times your third solution vector. And this is what your general solution would look like. Now, leaving your general solution in this form is fine. However, it's common practice to rewrite your general solution, factoring out your common factors of each column vector. So notice in our first column, we could factor out an e to the 3t. So we could write this as c1 e to the 3t times a vector of constants, 0, 0, 1. Similarly, out of the second column, we could factor out an e to the t times the vector 1, 1, 0. Out of the third column vector, we'll factor out an e to the 2t times the vector of constants, 2, 1, 1. And this is what we'll see as the more common form of our solutions. However, both are equivalently the same. Now your homework will also ask for you to write what is referred to as a fundamental matrix. For this system of equations. And what they're asking you to write is a matrix composed of your three solution vectors. So we want to take these three solution vectors and write them into a single matrix. So it would look like zero, 0, e to the 3t e to the t, e to the t, 0, 2e to the 2t, e to the 2t, and e to the 2t. Now we don't actually do anything with our fundamental matrix, but it does represent your matrix of different solution vectors that are there. So I want you to be prepared for it when you see it in your homework. Let's look at another example. Here we're asked to rewrite each vector equation, well there's only one, as a system of equations. So here we note the vector x is actually going to be the vector of two functions, x and y. In which case, this system of equations can be written as xy prime equals 1, 3, 2, negative 1 times our vector x. And to write this as a system of equations, let's take the derivative of each of our functions inside our vector. So this will be x prime, y prime. And on the right hand side, we'll just complete our matrix multiplication. And so again, as before, the way we'll do our matrix multiplication is take the first row of our matrix A times our column vector. To get x plus 3y. Similarly, to get our second equation, we'll take the second row of our matrix A and multiply it by our column vector. This will give us 2x minus y. And this is our system of equations that is equivalent to our matrix equation that was given to us. I have one last example for us to look at for chapter 6.1. And here we get to think about the Wronskian again. Recall the Wronskian is used to determine if a set of functions or a set of vectors is linearly independent. So here we're asked to use the Wronskian to show these vector functions are independent. Now to take the Wronskian, I am going to rewrite this matrix. Or rewrite these vector functions, excuse me. Rewrite these vector functions as, I'm just going to distribute the e to the 3t into this first vector. So e to the 3t, e to the 3t. And our second vector is going to be 2e to the negative t, negative 3e to the negative t. And we want to determine if these are linearly independent. So let's look at the Wronskian of each of these vectors. By creating a single matrix where these appear as the columns. And because our matrix ends up being a 2 by 2 matrix, we recall that the determinant of our 2 by 2 matrix is the product of the main diagonal minus the product of the off diagonal. So this will be e to the 3t times negative 3e to the negative t minus the off diagonal e to the 3t times 2e to the negative t. And let's simplify each of these terms. The first product, e to the 3t times negative 3e to the negative t, I think would be negative 3e to the 2t using rules of exponents. And our second product will be negative 2e to the 2t, and combining these terms we'll get negative 5e to the negative, or not negative, just e to the 2t. Notice that this is not equal to 0. Thus we can say these vectors are linearly independent. And sometimes we also say they form a fundamental set. Okay, this is all that I have for you for a lecture video for Chapter 6.1. Chapter 6.1 just wants us to introduce to systems of differential equations and what solutions look like. I hope this video is helpful, and I'll see you in our next video when we look at Chapter 6.2.